Hello, this is Black Hole Lab, and we're gonna start defining what is our goal in this lab. So we need to find the mass of a black hole which is interacting with a star. And for this we have a CSV data for the trajectory of that star. Another information that we have is the mass of the star, that is 1.98 plus 30 kilograms, and the position vector of the black hole that is in the origin of the data about the star's trajectory. So in this slide I have plotted the star's trajectory that if we observe, we can conclude that this star has an elliptical trajectory, and we have the black hole in the origin of this system. After making any conclusions, one important thing that we need is to define our system, which in this case is the black hole and the star. In the Python program, I need to define some things about the system observation. In this case, I define the star's mass and the black hole position and the time of the trajectory of the star. Now, this part is the main study of the motion of the star. Here we define the initial and final momentum, and because of that we can obtain the dp/dt and dp/dt parallel. So from this we know how to obtain the value of dp/dt perpendicular, and then the net force and its components perpendicular and parallel, which is by the subtraction of dp/dt parallel from dp/dt. So we obtain the result of the black hole mass from this part of Python program, which is the Newton's law of universal gravitation. So I obtain the value of the black hole mass is 1.98895 plus 31 kilograms. Here we have the code to obtain the black hole's mass, which is Newton's law of universal gravitation. If I run the Python program, we can see the star's trajectory and the Python shell that shows the final result of the time, the black hole's mass, and the net force parallel and perpendicular force. So we have the trajectory of the stars around the black hole. So in this simulation we can see the F net force, that is the yellow one, the perpendicular net force, that is this blue one, and the black one is the parallel net force. So if we see the trajectory of this star, we see that this parallel and perpendicular force is changing around that trajectory. So here we have our result about the black hole mass. This is the I show in the slide, and these are the F net force, the parallel force, and the perpendicular force. So here we have what we obtained for the Python program, that is the data that I have set. So in this part we have what does it mean. These are parts of this trajectory that are important. We can see in this picture that in this part of the movement we have the maximum velocity, and this occurs when the parallel component is 0. This part tells us that the velocity is maximum. The reason of this is that velocity is only changing in direction but not in magnitude. We can see the changes in velocity in the graph that is shown. That is a graph of momentum versus time, and we can see the changes in velocity in this graph. We can see that the parallel momentum is 0 because the trajectory in this part is nearly equal to to the circumference. So in this case, we know that it's changing just the direction. And when the star is far from the black hole, the Kissinger circle has a greater radius. And for this, the value of the perpendicular momentum is getting smaller. That is in this part. And for this, because the Kissinger circle has a greater radius, we have a minimum velocity. The velocity of this system or of this star is decreasing. For the velocity versus time graph, I obtain the values of the maximum and minimum velocity. The maximum velocity is 35617 meters per second, and the minimum velocity is 13612 meters per second, which is maximum when the parallel momentum is 0 and minimum when the perpendicular momentum is decreasing for the trajectory far from the black hole. So in this part of the picture, we have an increasing velocity because the F net force is in the direction of the movement. And here we have a decreasing velocity because the net force is opposite the movement of the star. So for the what if question, imagine the black hole whose mass you found was replaced by a different black hole but still placed at the same location. So we can determine the value of the new black hole mass and the gravitational force caused by it is different because it is directly proportional to the product of the mass of the star and the black hole, even though it assumes the same trajectory. Thank you.